Hi, my name is Duncan Hazel, and this is my physics extra credit lecture presentation. The lecture I went to was How Networks Drove the Rapid Revolution of Early Life, Clues from Canonical Genetic Code, that was given by Nigel Field. And the main points of this lecture are basically, he discusses the basics of DNA, like GUACT, and how it all fits together. And then he talks about how you're taught in like freshman biology that all the extra stuff that is like long, there's DNA is really long and there are very few like parts that actually code, but all the parts that you don't really care about that are basically the same for all organisms are very, very important to life itself, and like the intricacies and the way these like the canonical genetic code interact with each other and with the genes that actually do the UGACT actually interact with each other are essential to life itself. Like without DNA, I wouldn't be talking to you. I wouldn't be doing this. I might just be a roundworm for all I know. Like there are some really interesting facts I learned from this lecture. For example, like I guess most people do know that like basically most of our DNA, like something like 90% of our DNA is exactly the same as like say a frog, or an ape is like 99.7 or something. Those are some interesting facts. I also didn't realize how much bacteria is in our body. He used this as an example in the lecture. Like he was talking about how, like as an example of evolution, they studied bacteria, and like in 10 years there's as many bacteria in your body as, or there's, what is it? Let me look it up real quick. The amount of bacteria in your body is 10 times the amount of people in the world in one person. So that means like there's billions and billions of bacteria that grow in your body, and so it's great to study evolution. And so his main points, with some other interesting things I found was like he talks about patterns in code that like usually come up a couple times, or like clustering, where certain certain things like the U or the guanine or the CAT, they cluster together depending on like the organism. And I thought they're also like hydrophilic and hydrophobic. So that was really, I didn't remember learning that in biology, and I thought that was a really cool thing. Also, I forgot that like basically genetic code is in a bell curve. Basically, like most DNA is very, very similar, and then they're it's in the main part of the bell, like a grading, like being in grade, and then there's like very few that are really far to the right and very few that are very far to the left. And this is because of it's on purpose. He made a really important point to say that it's on purpose, because if it wasn't the same, then there wouldn't be life. He like hit on that a ton. The physics of this is basically like just it's a whole system. Like all these things, like the genes, the canonical genetic code, they all interact together to form a dynamical system that work together to put it together a living being like a human or a worm or a frog. Let's see. I mean, I took biology in high school and I really enjoyed it, which is one of the reasons I wanted to go see this lecture, because it sounded really interesting. Like baseball was tempting, but I'm like, everyone's going to go to the baseball lecture. I want to go learn something new that I'm not going to like. Who gets to go to a genetics lecture other than if you're at like Georgia Tech? So, in conclusion, like the main things that he hit on were the dynamics of cooperative, like all the genetic code and genetics, genes working together to form a human being or living being. It's called like cooperativity, and there are 3 phases of evolution: weak communal, strong communal, and then individual evolution, and it comes from like mutations and all that stuff. So I hope you learned something in this rambling, and have a good day.